I'm going to show you, I'm going to describe our simple model for friction. But first I'm going to start with a example, just a situation that you can have in your mind. So it's going to be a somewhat complicated example. I'll put it over here. So the idea is I've got what's often referred to as a inclined plane or wedge. So at inclined at some angle theta, it is on the Earth, and so this inclined plane is in the Earth environment, and so that means that there is an acceleration due to gravity that's downwards at 9.8 meters per second squared. What this means is that objects on the surface of the Earth have this weight force that's going to be acting on them. So I've got a wedge, and I've also got a little box that's on the wedge up here. And their surfaces are in contact with each other. So in our simple model, what we want to study is what's called contact force. And a contact force, I'm going to say, has the symbol C. And we can study the contact force that acts, say, on the box by the wedge. So that contact force is acting upon our box. But we could also study the Newton's third law of pair force, which is on the wedge by the box. So these two things, they are equal but opposite forces. They are action and reaction in the contact interaction between these two objects. You notice that I'm not talking about the Earth at all, but I could talk about the contact force between the Earth and the wedge. But the Earth and the box, they're not in contact, so their contact interaction is zero, and the forces involved are zeros. But anyways, let's talk about where I drew this little red squiggly line. So let's say that the box is, it could be sliding down the wedge right now. It could be actually sliding up the wedge because somebody, say, pushed it up the wedge and it's under its inertia is trying to keep going up the wedge. But let's say that or a third case would be the box is actually stuck on the wedge and nobody's touching it, and this box seems like it's sort of welded to the wedge and is stuck still statically. So it doesn't really matter, but I'm going to go in and draw a contact force on the box. And this contact force, I'm going to draw it in a particular way. I'm going to draw it like, so here's somewhere in the center of the box, representing the box kind of in a free body force diagram style. I'm going to say that the way the wedge pushes on the box, so this is on the box by the wedge, is like this. This is the situation of how the wedge is pushing on the box. And I'd like you to notice that this red arrow is it's not quite perpendicular to the wedge or the inclined plane, but neither is it all along the plane. It's something in between. So let me draw a line that's normal to the plane and a line that's parallel to the plane that's meant to be quite suggestive. So this contact force, C, can be thought of as a combination of something that is perpendicular to the wedge's surface. This is called the normal. And C is also partially made out of something that's along the wedge. so that's parallel. So down here, I'm going to say that this contact force on the box by the wedge is this red arrow here. It's actually the combination of a normal force on the box by the wedge plus, so that's the normal component, plus something else that's a part of the contact. And this something else is called friction. So I'm going to use lowercase f. I'm not sure what's in your book that you're using, but this is the friction on the box by the wedge. So what we do, like earlier in an earlier video, I modeled for you what's meant by the normal or support force. And I said in one of those earlier videos, this is because these two objects, we want to consider them as solids, and we don't want them to, and they're rigid, and we don't want them to overlap. And so whatever the normal force needs to be such that they don't overlap their volumes, that's what the normal force is going to be. This is the idea. Friction is just the other piece of how two objects can have a contact force. I can take my hands and I can push them directly at each other, or I can try to cause them to slip. So can you see that I have like that slipping action is along the surfaces, but then I have also a pressure or a push, like just it's hard to show you, I guess, but anyways, so yeah, and then down here, interestingly, let me fill out what's happening back on the wedge. So this is the contact force, this red C that I drew, it's all the upper stuff. But actually on the wedge below, just because of Newton's third law, I've got precisely, exactly the same but opposite contact force. So the box pushes inwards on the wedge, but also downwards. Down to the left. So it's got exactly a Newton's third law pair to the normal. Plus also a friction that's on the wedge by the box. So it's yeah, then Newton's third law even happens to the components of the vector. So this is the beginning of thinking about friction, and all of this that I just described is true in the static case or dynamic, also known as kinetic case. The static case, you probably heard me just a second ago say it was the stuck case. So static means that these two objects don't have relative motion, or a better way to say this is their surfaces, the two individual surfaces do not have relative motion, so they are stuck to each other. The dynamic or kinetic case is the sliding. So sliding means that the two surfaces do have relative motion. So these two cases, this is what I need to go on and explain next. So the static versus the kinetic